Hey, thanks for the intro, Gavin. Great to be here this morning. So appreciate Gavin's introduction. So just by way of background, I started out in the high accuracy GPS business in about 1989, 1990. When my boss came to me back then, I was working for a company called Corvallis Microtechnology in Corvallis, Oregon, and he came to me and said, hey, we have to get into this business. And he threw a copy of GPS World on my desk. And at that time, GPS World had just started publishing. And in fact, GPS wasn't even declared operational yet. And so that was my intro. And we were supplying handheld data collectors to GPS receiver manufacturers. And then we decided, hey, let's get in the GPS business. And about that time, Magnavox and Rockwell and a couple of others introduced small GPS receiver circuit boards that you could integrate into your products. And so we ended up integrating a 6-channel Magnavox receiver into one of our handhelds and created a product called the MC GPS in about 1993, 92, 93. And remember back then, and you think about and it was built for mapping, and back then mapping grade accuracy was sort of 2 to 5 meters, right? And that was after post-processing, because that's before President Clinton turned off selective availability. So if you just took your receiver and went outside, your accuracy would sort of be in the 50 to 100 meter range. It was not accurate enough for mapping, so you had to perform post-processing with your data to get it down to that 2 to 5 meter range. But they also had a carrier phase measurement engine in it, and so we could actually do some centimeter grade post-processing. But it was all post-processing. That's my point. And it was only 6-channel because it can only track a maximum of 6 GPS satellites at a time. No more. I mean, it's crazy to think about today when I take a receiver outside and I can track 30 to 40 satellites at any one time. So anyway, so I did that for 10 years. I was a product manager. We built lots of different sub-meter and RTK products, and wrote the software for the data collector and the PC side for processing. And in 2000, I decided to leave that company and start my own consulting firm. And I ended up doing a lot of mapping myself. I'd go out in the field. I mapped so many golf courses and so many accident reconstruction scenes using RTK primarily. And RTK was pretty early back then. RTK was only developed, mid-90s. And so it wasn't that old, and GPS only made it even more challenging because you had a limited number of satellites. I remember doing projects up in Lake Tahoe with 200-foot trees around me and trying to get a fixed solution on golf greens. And so we're come a long way since then. So my discussion today is I'm going to talk about 3 major trends, I think, in high precision GNSS, and Gavin's kind of teased you on those. But what I wanted to do was to show you something interesting, and some of you may have remembered this publication from a long time ago. This is Geo World Magazine, which isn't published any longer. And so I wrote an article for Geo World Magazine, and it's right here. It's a picture of a Trimble Recon, or a TDS Recon back then. And the article is titled GPS Mapping Comes of Age. And so my trends back then, so I wrote about a few different trends at that point. And they were, one of the trends was Bluetooth receivers. Because back then, Bluetooth receivers were just being developed. And Bluetooth was a little bit flaky back then. And it wasn't, most of the implementations weren't that reliable. Some were very good. So I wrote about Bluetooth being sort of a big innovation because it's going to separate the data collector from the GPS receiver and give you lots more flexibility. So as data collector technology evolved, you could change. For example, you go from a Recon to a Nomad to a different kind of Windows device. And back then, remember, iOS and Android didn't exist, and so you were either going to use a Windows tablet or which the battery life was horrible, or a Windows mobile handheld device. And so the trends back then were Bluetooth, and then these rugged mobile devices running Windows Mobile. And then the third piece of the puzzle was SBAS back then, which WAS. And remember, WAS was introduced in 2003, about officially declared operational. And with WAS, you could get in real time sub-meter accuracy. And this was big for me back then because, you know, I had spent the last 10 or so years helping develop post-processing software to get sub-meter accuracy in cases, but even more than that in most cases. So now we're able to take a receiver outside and free of charge turn on and get sub-meter accuracy out of the system operated by the FAA. So that was a huge trend towards real time. And that was when, you know, I said to myself, I never want to go back to post-processing again, at least in a production standpoint. You know, you can do it for setting opus points and control and that kind of stuff. But in terms of collecting data in a production mode, you know, once you do real time, it's hard to go back to post-processing. So it was exciting. So that was in 2004, Geo World Magazine, as I wrote that article back then. So it's really fun to think about how things have evolved since then. So now I've got, you know, it's 2020, and I've got three trends to talk about, and I've written about these somewhat in the past, but I want to go over them in some detail. So the first thing is just a glossary really quick. I know this is old news to some of you folks, but I just want to make sure we're all clear when I tend to throw these terms out, that we all have a common understanding. So when I say mobile device, I'm talking about the mobile device running iOS, Android, or Windows these days. When I talk about GNSS, I talk about, that's the sort of GNSS is the generic overall term for all the different systems throughout the world. I mean, you know, back in 1990 when I just started, it was, you know, GPS was the primary, and GLONASS was being developed about the same time, but that was it, right? But now we have, you know, GPS and GLONASS, Galileo is the European system, and then Beidou, which is a Chinese system. Those are the four global constellations. There's mention of QZSS and others, and IRNSS in India, but those are all regional constellations that don't help us over here, so at least in the US. And so I tend to focus on those four constellations. And then when you talk about survey grade, you know, I refer to RTK, which is real-time centimeter accuracy. You get you 1 to 2 centimeters horizontal, 3 to 4 centimeters vertical precision. Mapping grade is using DGPS, like the article I showed you I wrote 16 years ago. That was all SBAS or WAS DGPS. That's sub-meter accuracy with the right kind of receiver. And then lastly, when I talk about workflow, I talk about softwares that enable hardware to efficiently complete a task. And that's really the glue that brings things together, because if you don't have the right software, the hardware just doesn't work. And I remember back in college, you know, when I didn't, you know, this is probably back in 85, 86, when I'd start up an IBM computer back then, or IBM PC, and then you have to figure out what kind of software you want to run, because just a computer by itself on your desk didn't help you at all. So anyway, those are some common terms. So the first high accuracy I call mega trends is obviously GNSS, right? And that's the one that's changed a lot over the past few years. In fact, I have in some other presentations I've made the statement that GNSS has changed more in the last 3 years than it has in the last 15 or 20 years. And it's incredible. And really the main reasons are the addition of the new constellations, and primarily Beidou and Galileo. I mean, GPS and GLONASS have been around forever. GLONASS has had its ups and downs, but it's pretty stable, is stable. But the new ones are Galileo and Beidou, and especially Beidou has launched a crazy number of satellites in the past 3 years. I mean, almost from nothing up to, you know, 20, 30 satellites. This is a great slide from UNAVCO that I use just to give you an idea or a context of where the orbits are in these, and how they don't collide, I guess is some way to put it. But anyway, so to just give you an idea of what the orbits look like compared to the space stations. You know, you don't think about this with reference to the Hubble or the space station, but how much further out the GNSS satellites are. And the amazing part about it is they're super weak signals, and I've seen the comment that it's about the signal strength of a 50-watt light bulb from, you know, 20,000 kilometers in space. So I just think that's a neat slide to look at. So here's the magic, and this is where it really would have helped me, you know, 18 years ago down in Lake Tahoe when I'm mapping this golf course at Incline Village with all these tall trees around. Back then, I was only working in this area here, this green area with GPS only satellites, and so I'm fighting you know, I'm tracking anywhere from probably 5 to 8 satellites, you know, when I'm trying to map this golf course. I'm trying to dodge players and be respectful and that kind of stuff. But boy, if I would have had, you know, I didn't even have GLONASS back then. This was really early on. I had a GPS only receiver, and Galileo and Beidou. It really would have made a huge productivity difference. And really, that's what 4 constellations is all about. It's not about accuracy. It's not because you're going to get better accuracy out in the wide open because you have more satellites. It's all about productivity. You're able to work in tougher places that you couldn't work in before, up against buildings, under tree canopy, near tree canopy, and rugged terrain, that sort of thing. And this is an example. I booted up a receiver yesterday in our lab and just without doing anything, just booted up and using our roof antenna. And this is the number of satellites I was able to track. And granted, this is clear view sky because it's a roof antenna. But boy, even if you had half of that, if you're out there working, it's amazing the number of satellites we can use today. And they're all mature now. I mean, I think Beidou and Galileo have more or less finalized their constellations, or maybe 1 or 2 more here or there, but for the most part, they're finalized. And this is a plot in Portland, Oregon, on the left of today from 8 a.m. to 8 p.m. of the number of satellites in view or in view that you could use. And I think it's based on a 10-degree elevation mask even. So anyway, so this is really the primary reason why high accuracy GNSS is changing more than ever before in history. It's just so many more satellites available for high accuracy positioning. So, and what Gavin said is true also, is you can, you know, once you start to be able to work in all these more places and you have the software to glue it all together, you can start to put this in the hands of interns and technicians that can map a tremendous amount of assets really accurately and efficiently. So this is a really kind of a cool slide for me because it emphasizes how complex the 4 constellation signals and frequencies are. And I'm not going to go into a lot of detail on this because it's you can probably spend a half an hour on it. But just to give you an idea that with a range of frequencies that are being used. So on the right-hand side is the typical L1 receiver that's in your vehicle or your phone. It uses GPS and GLONASS typically. Some are offering more constellations than that. And on the lower bands, those are the multi-frequencies. So you know L2 and L5, and there's a whole series of signals and frequencies that receivers are able to exploit. And what I really want to talk about in this area, because what's interesting is that receivers, you can have a 4 constellation receiver, but it doesn't mean that it supports all the signals and frequencies in that constellation. So you got to be careful, I guess is the right term, when you start to think about, you know, which receivers, I guess, to purchase or whatever. What do you expect? Just make sure your expectations match. Because, for example, up in you look at this list of different frequencies, and I hope I got them all. I'm sure you'll hear about it if I missed some, but just, you know, Beidou alone, BDS. I mean, look at those different signals, and not all receivers can process all the data from those signals, and so they end up picking and choosing which of these to support, right? So I guess my point is, and here's a good example, is that, you know, the car manufacturers are heading towards mass deployment of RTK. And you may have heard about this for autonomous driving. And of course, they are very interested in low-cost receivers and low-cost antennas for dual frequency or multi-frequency RTK. But they've only typically, at least the receiver manufacturers that are chasing after that market are only only supporting typically L1 and L5, or E1 and E5 for Galileo, because it ends up being a simpler receiver, and maybe it's mostly driven by the antenna on the roof. Because if you look back at the range here, if you wanted to cover all these different frequencies, you can't do it with a dual frequency antenna. You can't even do it with a triple frequency antenna. You're talking about 4 different antenna elements, maybe even more than that. And so in the car manufacturers, as you can imagine, they're trying to get the cost down as much as possible. and they try to fit everything in that shark fin antenna at the top of your car. You've seen those, right? You look at the top of a car and you see that sort of shark fin looking antenna. They're trying to fit all the antenna elements within that shark fin, and you can fit 2 of them in there, L1 and L5, but really can't fit 3 of them in there. And so I don't know if that's a decision driver for them, but that's certainly one consideration to have, because they, car manufacturers are insanely price sensitive, and if you talk about adding 10 or 20 cents more, they get really upset. And so RTK in cars is not going to support this whole range of constellations and frequencies. They're going to pick and choose the ones they want that they can most efficiently deploy, that will be as effective as they need to be to provide that accuracy that they want. And by the way, car manufacturers aren't interested in centimeter accuracy. They're interested in 1.5 foot accuracy, or they call it lane accuracy, a foot and a half. But if you want that reliably, then you need to be down at the centimeter level and allow for outliers and so on. So anyway, that's a point. So if you look at all the receivers, especially inexpensive receivers being introduced, RTK receivers, you look at this whole spectrum and you find that they may not implement the entire complement of frequencies and signals that are offered. And the reason I have E6 emphasized there, E6 Galileo, that's a very interesting one. And I don't have a lot of time to talk about it. But Gavin mentioned PPP, real-time PPP, which is using geosynchronous satellites to work anywhere in the world to get you down to sort of sub-decimeter accuracy, right? And if there's been lots of discussions yesterday, I think here and probably today too, about real-time PPP and the deployments of it. And it's been used for decades. It used to be OmniStar, now it's RTX, and there's Atlas, and there's TerraStar, and lots of other services out there. But Galileo is introducing a similar service, PPP real-time service, that's free. All those other services I mentioned are paid subscription services. But Galileo is introducing a high accuracy service that's going to be broadcast free from Galileo satellites that will get you sort of down in that 20 centimeter range without any connectivity to wireless network like RTK, just linked up to not even geosynchronous satellites, but Galileo satellites. Each Galileo satellite will be broadcasting this E6 high accuracy service. And so you don't need to worry about having a clear view of the sky to this geosynchronous satellite like you do with these other services that are discussed. This is broadcast from each Galileo satellite, and there's upwards of 20 to 30 of them up there. So as they cross the sky, you can lose one and pick up the other and still receive this correction. To me, that's the most interesting thing about this service, is that we're not limited by geosynchronous visibility. We have visibility across a bunch of different Galileo satellites for that high accuracy correction service. It's not available yet, but it will be soon. And but you will need a receiver that supports that E6 frequency, right? Which is different. So it's probably going to take another antenna element, is my guess. So it's a complicated. That's the reason I titled this slide. It's complicated because it is. I mean, this is probably a half a day discussion, just sorting through all these things here. So I'm going to move on because I don't have all day to do that. But here's the question, I think, is how far can we push for constellation GNSS, high accuracy for constellation GNSS in these kind of environments, right? And these are a couple pictures I took out in different projects. This one on the left is an alleyway with 4 stories, and it's got some gas infrastructure inside there that the utility wants to map. Can 4 constellations work in that environment? The picture on the right is a picture in Manhattan, in New York City, with these huge buildings, 70, 80, 90-story buildings. You can barely see the sun sometimes. Does 4 constellations work in those environments? And the answer is sometimes, but even 4 constellations have a hard time working in that environment. So it's not the end-all answer, but if you talk about working in backyards, in residential areas where there's trees in between 1 or 2-story buildings, yeah, 4 constellations helps you achieve high accuracy in those environments where you couldn't do that with GPS only, or even GPS GLONASS. I'll have a more discussion about this kind of environmental challenges here later, because we have other different augmentation technologies that we can use. This is just an interesting test course that I had set up last year. I had a surveying intern with a robotic toll station set up a bunch of control points out in different varying canopies, tree canopies, because I wanted to understand how much of an advantage having 4 constellations would be over having 1 or 2 constellations. And I have a day-long presentation I do on this test, but I'm just going to briefly hit on it. But here's an example of we have a camera that we shot straight up in the air to sort of characterize the density of the tree canopy. So we ran a bunch of tests. I ran a crew, 2 crews through this test course for an entire week. We collected about 1,000 data points on 20 some odd different control points under open sky, light canopy, medium canopy, heavy canopy. This is one of the heavier canopy, these pictures right here. And at the end of the day, roughly, we concluded that 4 constellations was about a 50% increase in productivity over 2 constellations in that kind of tough environment. And so when I start talking to companies that want to deploy RTK, I started talking about productivity because they talk a lot about capital cost of equipment, and I remind them that operational cost can really be really expensive, and if you can spend more capital money up front on equipment that's going to be more efficient, then you can save a lot more operational costs, especially if you start talking about a project that's 2 or 3 years old or in length. You can save a ton of money in the field by saving field time. All right, so that's the discussion on GNSS, and I've got a couple other things sprinkled in here too. So that's the first sort of megatrend, the whole transformation of the whole GNSS space in the last 3 years, especially. And it's amazing how much has changed. And I'll actually have another slide in here too about dual frequency chipsets and phones, which I'll touch on, but I didn't put it in this part of it. But I wanted to move to the second megatrend, which is this term that Gavin had mentioned called BYOD, bring your own device. And this has been a huge transformation. Remember these? This is, I used to own a Nomad, right? And use it for data collection because we'd pop a Bluetooth CF card in the top of it and Bluetooth to different receivers. This is, that article I wrote back in 2004, I talked about that. And then BlackBerry was the king, of smartphones back, in the late 2009, 2009. Nokia was a major player. I mean, where are these today? They don't exist, right? Or barely exist. I think I may have a Nomad still around here, but certainly I don't have a BlackBerry or Nokia. So this massive transformation started in about 2010, about 10 years ago, was this morph towards, Apple and Android and Windows 10 lesser, but mainly Apple, iOS, and Android are just dominate the mobile device space these days. And it causes huge rift in the industry because all this software for asset data collection was written around Windows and Windows Mobile. And it's a pretty serious task to migrate that software over to iOS or Android. And just some kind of cool slides that I wanted to show really quick is this mobile device market share. So you look at operating systems market share worldwide. The orange line is Android, and the line below that, and I know the colors are kind of hard to see, I think it's green or a dark green, that's iOS. And this is a 10-year span. This is from January 2010 to September 2020. A 10-year span of what happened to mobile devices. You look in the beginning, back in 2010, iOS and Android really didn't have much going on. Well, Android did, or iOS did a bit, about 32% market share back then. But if you look back at 2008, you can go back further, iOS was nobody back then. And you look at how Android's taken off. Remember, this is worldwide market share, not US, this is worldwide. So today, Android has about 74% market share worldwide mobile devices, iOS has 25%, and the rest are just sort of other, insignificant. Then if I look at the US market share, it's fascinating. iOS owns 60 or 59% market share, Android has 40, and then the rest are just other, right? Then the US and the world are kind of flipped in a way. The Americans really like their iOS devices, their iPhones. and then so just some pictures of different configurations of these mobile devices with high accuracy GNSS receivers. So on the left side, you have a catalyst with the Trumbull catalyst with capable of centimeter accuracy with a mobile phone. In the middle, there's an iPhone with an Aero receiver on the back of it and a handheld config. On the right side, there's a 5-pound, and that's complete with the range pole and the iPad on it, getting RTK type of accuracy. So it really, the whole BYOD approach gives a ton of flexibility because you can Bluetooth to the receiver and have all different kinds of ergonomic configurations. So cost-wise, you look at, that's me on the left back in 2005, and this was actually in to Lake Tahoe, work on the project. You imagine GPS only with those trees around you, the efficiency was brutal. I probably could have completed the project in a quarter of the time if I'd had multi-constellation, and it was expensive. That receiver setup cost me, I think $30,000, and I got a really good discount on it, $30,000 back then for a base and rover configuration. But wait, you don't see it, but on my back there is about a 20-pound backpack with batteries and a big receiver and a radio, UHF radio, and so on. And on the right side is that's a 5-pound setup costing well under $10,000 using an iPad that's $500 that if you break it or lose it, you can just pick up another one and keep on going. So that's the big deal. Cost down. It's almost like Moore's law. Things get better, faster, and cheaper over time, and we certainly see that in the GNSS industry. And I just threw this slide in at the last minute. By the way, what happened to this? Remember Broadcom launched a dual frequency GNSS chipset back in 2017, so 3 years ago, almost 3 years ago this month. And people said, hey, all of a sudden you can have, decimeter accuracy or centimeter accuracy in your phone. And it never really came around to be true, right? And I think the bottom line is that the phone companies really don't care about high accuracy. I mean, they're not going to put a better antenna inside there, and maybe the antenna ends up being the biggest constraint because in their minds the antenna is a trace on a PC board, or they share it with Bluetooth, and they really don't give it much respect. And so if that ends up being the weakest link, that's like putting bicycle tires on an Indy race car. It's only as good as the bicycle tires, even though the engine can create 1,000 horsepower. So it never really came to fruition, this Broadcom chipset inside these phones. And now maybe they will. In fact, I think they will eventually, but is that 5 years out, 7 years out, 10 years out? I don't know. The phone manufacturers aren't really interested in investing in high accuracy space because it's a pretty limited crowd. And unless there's a killer app that's developed that will be attractive to consumers, tens of millions of people or 100 million people, they're really not going to be interested in supporting high accuracy, I don't think. So the third megatrend, the last one, is software, right? And software glues all this stuff together. Remember I told you when I was back in college and I boot up my IBM PC, and it was nothing. It was just a command line with a C prompt and DOS, and you had to boot up a database software or a word processor or a spreadsheet or whatever to make it useful. And it's the same with this technology, with GNSS technology and mobile devices. They're worthless to us without the software. And I'm probably going to get beat up on this, but I'm going to sort of fly the ESRI flag here because they've done some great things in the past few years. And this is sort of their ecosystem right here. On the left side, you see Collector for ArcGIS, which is their mobile device for collecting data. Survey 123. There's others in there. Quick Capture that have been introduced. Field Maps has been introduced. So they have this whole ecosystem of different mobile data collection softwares. And some of you say, man, yeah, well, whatever. Esri's been around for a long time, ArcPad and so on. But they really have made a huge step in making high accuracy available to almost everybody in the past few years. And it's shown by this. Here's a slide here that shows you the adoption of Collector over the past 6 years. Or 7 years. Collector was introduced in 2013. You can see where they added GPS averaging in high accuracy GPS in July of 2016. And look how it's exploded. It was 304,000 logins or users downloads back then. Now it's up to 1 million. In fact, it's even higher than that because this slide's about a year old. So if you look at how many downloads they've had of Collector Classic, which was a 2D version of Collector, they had a 1.6 million downloads of Collector Classic, and that's a 2D program. Collector, the current Collector is a 3D, so it's XYZ, 1.5 million downloads since December 2018. And it can get you survey grade, horizontal, and vertical accuracy with even geoid model support. And if you look at this slide down here, this is logins per day of Collector, and this is in September, so I just got this week. For the previous 12 months, in fact, you see, you know, Christmas time and there people aren't logging in, but you see daily login activity. You can see where coronavirus sort of caused a problem in here, but it's up to, you know, 23,000 or 24,000 logins of Collector. Now, these aren't all high accuracy users, obviously, but it shows you the adoption and the power behind this platform. And it's really, since 2016, Esri has put a lot of energy into supporting high accuracy receivers, horizontally and vertically. And so you can easily field a crew to go out and collect survey grade accuracy in that environment. And here's an example. This is a vineyard project that I worked on down in California. They're running, actually in this case, they're running Quick Capture, which is a sister program to Collector. And the reason we use Quick Capture is because we had to collect a lot of data really fast, 500,000 vineyard points, vineyard vines. And this is a person with this setup here. There's a high accuracy receiver. This is triple frequency RTK with an iPhone here in a handheld platform. And this is the kind of data they're collecting. So they're going, these are 3 feet spaced apart, and they want to collect them as fast as they can. So the travel time between these is about, or sorry, the timestamp between points here is about 5 seconds. We're collecting incredibly fast data at the centimeter level. You can see it here, horizontal accuracy and vertical accuracy, about centimeter both. This has got a base station, an RTK base station on site, and so the baseline is really short. And I think, yeah, and here's a really cool scene, a 3D arc scene. This is what's cool about the whole Esri environment to me, is that you can have a crew of 5 or 10 people out there, and then back in the office, you'll be able to see the data as it's collected in real time. And so if you see a problem or people are not coordinated well in the field, you can be back in the office watching all of them work as the data is populated, and then create kind of really cool scenes like this one. This is a 3D scene. I'm going to flip, well, I'm not going to do it. I don't think I have time for that. I'm going to speed through a couple more slides here. But anyway, it's a really cool environment. And this is, in this slide, I'm showing that this is one of the base stations that we deployed on that vineyard project. But, you know, with this whole new GNSS evolution, you can create all your different kinds of base station configurations. People used to think that base stations were super difficult to deploy and manage and maintain, but you know, we've deployed some really interesting stations. One on the left is a wireless modem here with a static IP on it. You can put an antenna on a tripod and a triple frequency RTK receiver. Over on the right here is a fixed mount you can put up on a tower in your office to broadcast. But you know, really cool stuff. Now, this next slide for AEC is how do we overcome the limitations of GNSS in general? And I don't care if you have 4 constellations or even 6 constellations or whatever. There's going to be assets like this that need to be collected accurately, that you can't really get up to closely or efficiently collect closely to it. And so, you know, there's all these augmentation tools, or the sensor integration that Gavin was talking about and other folks is, and then one of them is laser mapping, using a laser rangefinder, reflectorless laser rangefinder to tap these. And this is all glued together by the software. This is made possible by the data collection software, being able to glue all these pieces together and make it an effective and efficient work solution. Same with this utility locating solution. This is a unique solution now, you know, a combination of EOS and Esri that put together the solution for making this whole locator solution Bluetooth to an iPad, and you can collect data in Collector, underground infrastructure data in Collector automatically, just with a push of a button on the locator. These are the kind of sensor integration things that we're going to see going forward, I think. Here's an augmented reality type of solution. You know, I think AR is really early right now, but as especially underground spatial databases become more accurate, they have to be, then I think you'll see augmented reality doing really well and making a big splash in the industry. And then lastly, I think the Esri Autodesk partnership is important. I think this is a quote from a couple of years ago. You know, Esri and Autodesk, they really didn't talk for a lot of years, but then they came together couple of years ago, and really to work together in the sort of CAD environment and GIS, making those things work together. This is what Civil 3D, I think they've got a plugin for Civil 3D to work back and forth between ESRI, and you can publish it to ArcGIS Online. I mean, there's some really cool projects that we're working on now where we're moving data back and forth between CAD and GIS, and it's still not where it needs to be, but man, I'm telling you, it's good. It's getting there, and you know, we over the years we've sort of you know, had this battle between GIS and CAD, or GIS and engineering, and I really see that gap is closing, and the tools that are coming out are really going to help us be really efficient in the way we collect and manage AEC type data. So Gavin, I think I did it. I got what, 11 minutes to go for questions.
Great.
I haven't been looking at the chat or the questions or anything, so.
Okay, well, here I'll start off with the questions in the order we got them. Okay. One is, would like to hear Eric's opinion on the time versus distance debate for accurate GNSS observations with the addition of all these constellations of satellites.
So time versus distance?
I wasn't sure about that.
So I think maybe my guess is they're talking about occupation time, okay, which is a valid question, right? So how long should you occupy a point? And it used to be, remember Gavin, back in the day, I mean, if you wanted to set survey control with RTK, what was it, like 180 seconds or something like that? I forget the recommended.
Yeah, people would either cook for 180 seconds or do multiple sets of short shots.
Right. And so in my mind, that the occupation time question, the occupation time has shortened in my mind. Well, and it kind of depends on what your goal is, right? So if in the case of that vineyard, there's no way we could have spent more than a second on it. There's no way, because but you also have to look at what's the downside, right? If I miss one, is it really that impactful? Not really. But if you have to collect 500,000 vine points, you're going to spend a ton of money if you're going to collect 10 seconds of data on each one, or even 5 seconds, or even 2 seconds. So we were just taking a second on each point, and it was it turned out pretty well. So it depends on the project and how efficient you have to be. For example, if I'm going to fly my drone and I need to travel 3 hours to a site and collect some GCP data, ground control point data with RTK, I'm going to spend an extra minute there because I'm only going to collect 5 or 6 GCPs, and I want to make sure I really get them right. So in my mind, it kind of depends. If you're in serious production mode, you can get by with as little as a second, as long as you're plumbed up and your data looks good. But you know, would you want to do that if you're doing GCPs on a site you had to travel 3 hours to? No, I'm going to stand there for 30 seconds, right?
Yeah, I agree. And you know, I do a lot of testing on this as well, and things in the past few years have just gotten insanely better on repeatability. I found out, as have others, that doing a repeat observation at a different time of day or a different day that we used to have to do a long time ago with one constellation is pretty well moot.
Right.
Even if I'm doing control points, I can cook down, and depending on the data collector software, if it's like running a common static filter and it'll sort of converge down over a period of time, a lot of them don't work that way. If something fixes within a few seconds, that precision, that accuracy is about as good as it's going to get, but you want to prove the repeatability. So in that 180 seconds we used to spend on control points cooking down and having to repeat that a few times, we can just do many shorter observations and look for the outliers.
So where I would take exception to my thought there was when we did the testing underneath heavy tree canopy in that test course that I showed earlier. We actually took 60 seconds of data no matter what.
Yeah.
And if I was actually using that for production work, I would hit those probably 2 or 3 times, not different times of the day, but I would actually go outside the tree canopy, reset the RTK, and then go back in and see, because even with 4 constellations, I think receiver manufacturers are still tweaking their firmware to be optimized in that environment. Because I've had bad shots in that, especially under the really extreme stuff. where the sky is really blocked, you can track quite a few satellites in there, and you could eventually get a fixed solution. But whether you trust that solution is the question, right?
Oh yeah, there's limits. There's limits, but the limits are getting stretched. That's for sure. Next question. Get to these real quick. Elazar asked, do you know if the actual GNSS receivers support all Beidou signals?
No, I don't think they do. No,
not all of them, not yet.
No, I don't think that a lot of receivers don't, because they didn't release their ICD, which was the interface document, until pretty late in the game, and so companies didn't know what to do. And so, especially look at the B3 signals. I think a lot of receivers out there don't support those.
Yeah, even some of the Chinese manufacturers, I've tried some of their gear out. They haven't implemented all of them yet either,
right.
But everybody intends to.
You look, it's gone so fast because, you know, Beidou launched a ton, probably 20 satellites over a 2-year period or something like that. It was some insane speed.
Mm-hmm. So second part of that question regarding the E6 PPP service, do you have any idea of when that might begin to be available? I know E6 as a signal is transmitted, and there are a few manufacturers that have implemented it, but not the PPP service yet.
No, PPP's. In fact, I sent an email to some colleagues over in Europe to ask, but I didn't get a response back this week. The last schedule I heard was it was going to be this year, but I hadn't seen any announcements. They still had to issue a contract to the vendor who was going to develop that service and offer it. But that was supposed to be fourth quarter last year. I didn't hear anything about that. So I don't know. I kind of doubt it's going to be this year, but I wouldn't be surprised. That's the original schedule I was told.
Okay. Well, and then to note that, you know, they've got that experimental signal on the QZSS over Japan where they're doing PPP augmentations over that.
So it's something to note that E6 is a different frequency, and so you're going to need a receiver that's specifically built to track E6, which is not common in receivers yet.
No, a couple of the big name manufacturers have implemented E6, but they're not doing anything with it yet. So, and
it's a different antenna too, right? You need a different antenna, different receiver and different antenna.
It had to be a different antenna, yeah, or slight you need those low noise amplifiers for each of those. So another question here, this was asked yesterday. When do you think the under $1,000 RTK level solution will become a reality?
So, under 1,000?
Yeah, that's tough.
Oh, I think it's going to be. I mean, it's already there today.
Sort of.
I think if you look at the car manufacturers, I mean, they want to pay $100 for.
Yeah.
I mean, that's just a raw board. That's just a raw receiver. That's not all the stuff around it. Because people think. Here's the challenge: is that the RTK part of a receiver isn't necessarily the most expensive part. It's all the glue and the stuff to put it all together and make it a reliable, robust system. The RTK component of it really isn't. You know, you look at Broadcom, you could probably buy a dual frequency chip from them for well under $100. But you know, the problem is when you start to integrate that into a system that's got to be robust, reliable, supported. And that's what drives the cost up. It's not just the cost of RTK itself.
Well, like you said, it's different verticals. You know, the automotive, they want to, you know, 2 frequencies. They're not aiming for centimeter.
Right.
And the antenna as well. So, okay, let's say you have $1,000 dual frequency RTK unit, and you have to slap a good antenna on it. So you're busting the 2,000. But the problem is that it's very limited in what you can do with it. It doesn't have other multiple frequencies. Probably can't get all the constellations.
Right.
It probably does not have. You have to have a hell of a lot of other things going on in there in the engines, multipath mitigation, you know, good antenna. I don't think for the purposes we're talking about for the asset inventory and survey and construction and AEC that the $1,000 receiver. I have tried out a $3,000 receiver that matched, you know, like a $22,000 survey rover.
Mm-hmm.
We are at that threshold, but they've done everything else right.
Mhm.
I mean, and then you look at some of the new U-Blocks chips. Those,
Right.
there are people that are putting those into rover type units, but
Right.
there's a lot of other moving parts involved to get something that's a reliable, robust field inventory type unit.
And I caution people who worry too much about capital costs versus operational costs that I mentioned before, because you can easily eat up any capital cost savings by inefficiencies in the field, especially in high labor cost environments like the United States. Let's say if you choose to buy a receiver for $6,000 instead of $8,000, so you save $2,000 on the capital cost, but then you don't have the support infrastructure or the software support or the reliability or the efficiency of the receiver if you just spent $2,000 more. You could easily lose that $2,000 in the first 6 months of inefficiency. So I caution people not to get too hung up on saving $100 here or there, or saving 500 here or there. Go with the system that's going to be the highest efficiency and production efficient type of solution. Even if it costs you a bit more out of the gate, you'll save it in droves during operations.
Cool. And we used to joke, over a decade ago, we used to joke about someday there's going to be the little puck peripheral for a phone.
Yes, we've been talking about that for years.
Years. Okay. Okay, this is a question I think we'll talk about at the end of the day, but if you're around, Eric, can there exist a world without GNSS? Can the different human tasks work without satellite positioning? Well, anyhow, let's just leave that one open for now.